This is our third presentation of virtual reality for data analysis. And what we're concerned with in this presentation is our current classification work, where our target of interest is the one class, and that's where the red dots are, and those are the class of interest. Perhaps these are biopsies that are not healthy biopsies, and we want to know if a new biopsy is cancerous or not, which is one of our data sets in the paper. And so the black triangles are true positives because they're well within the class domain, and the purple triangles are true negatives because they are outside the class domain. And any autonomous algorithm with with basic thresholds should be able to classify correctly. So what we're interested in doing in the virtual reality is taking those false negatives and false positives, which are on the borderline, the edge of the classification domain, which would put them on the borderline with any kind of thresholding. And these are the ones that even autonomous algorithms will give you false negatives and false positives, and we want to convert those, like I said, to true positives and true negatives. We're also working on multi-class classification situations as well. And in this classification work, as I noted on the bottom, we've noticed that with our virtual reality glyphs being how you represent your objects in virtual reality, that we can identify these local classes. And so that's also helpful in our one class classification, depending on what the target sample looks like relative to its spatial position in the VR and the local class surrounding it, the samples. So as I mentioned, this is our third virtual reality presentation. Our first one, they're both of the other two are on, you can watch a movie on YouTube and they explain it all. And they're based off our first one is a publication for model selection in transfer learning and other calibration type processes. And the second one, that is a manuscript out for review, and that's using virtual reality to do outlier detection. And these little blue spears with spikes, those are similar glyphs that we're using here in the one class classification. So we need to represent our samples in virtual reality. Like I said, these are called glyphs. And so what we are using are all the similarity measures, because we want to compare a sample to a sample. Our algorithm called physical chemical responsive integrated similarity measure, or PRISM for short. And in PRISM, we create two types of similarity measures. One we call PRISM X, and these are based off our measured feature similarities. And that's what we'll be using in the one class classifier, just PRISM X, so they're just called PRISM. And then we have PRISM Y that we used in the outlier detection paper, and that's where we base it off our estimated analyte amounts. So this is actually useful when you have unlabeled samples, such as in local modeling, is also where we use PRISM, and it can identify samples that are similar to your target sample based off the measured features and the estimated analyte values of your target sample. So we're going to use these PRISM X or PRISM values as our information streams for our VR glyph feature. Shown here are our glyphs that we're using, and it's a sphere with spikes like our outlier glyphs, and the spikes have 316 PRISM X similarity values, or just PRISM values, because like I said, we don't use any PRISM Y values. And the size are the sample-wise z-scores. We also use conformal prediction p-values to generate the sizes. In the color shading, we kind of double up on the z-scores and p-values. The color shading is it's light colored for a small z-score, or a larger p-value, up through dark is a large z-score or a small p-value. So you can immediately see not only in the distance, because because it's 3D, so those samples that are far from you, they appear small, and it's hard to know what the z-score actually is without zooming in on it in the virtual reality. So we color shade it, and then you can instantly see where the large z values are as well as the smaller z values. And like our outlier paper, you can touch each glyph and it'll pop up like it shows there what sample number it is, and the z-score and the p-value. So for the classification, it actually doesn't say sample number. It says if the sample came from the source, if it's a source or a training sample, and for and or it's a non-class sample. But it does give you the z-score and the p. In the VR, well, we have a UI, a user interface, and that allows us to change the view that we're seeing of our glyphs. So we're using principal component for our axes, but in the outlier paper, we also use UMAP. So you can see that on the left, we have slide bars, so we can create a plot with any PCs for any of the three axes. And then we have a scaling method where we range scale, or we also toggle to z-scoring. And the group value and color scheme, those are for our multi-class and local class work. And then we have our size method to toggle between z-score and like I said, the conformal prediction p-values. And then, as you can see, we have some analytics. It's telling us how many samples are in the training set that are being posted into the VR, how many target samples are getting posted into the VR. In this case, for this example, there are 6 target samples. And then this is one class classification. And targets, the slide bar on the far right, since there are 6 targets, we can slide around. It gets too confusing if you have all 6 target samples in the VR, so we use the slide bar to pick and choose which target sample we want displayed in the VR. And then the reveal target, because we are trying to convert false positives and false negatives to true negatives and true positives. And so we do have a reveal button to see, once we decide what is truth. So in the paper, we have 4 data sets, including some cancer one class classification data sets. But this one that we have a little short video on for typically what goes on in the VR is our QSAR data set. And so ultimately we do a bunch of different random splits because we're trying to find a data split where we have some false positives and false negatives to pick from. And there are usually too many. Like you see, we got 64 target. We end up with 64 target compounds with our splitting, and 32 active and 32 inactive. And so we can't have all 64 in the VR at once. And so we just pick 4 to 6 of them, and then we just use those in the VR and see how well we do. So this is the video of it. Again, it's never as impressive as the real thing. So there's the UI. Blue are training samples, red is a target samples. These right now are range scaled, the spikes. So all the spikes go between 0 and 1. And so what we're looking for is the spatially close samples with similar Z values to the target, as well as, and then we're going to look at the spikes for their pattern, basically how big and small they all are in their relative positions, corresponding to the different similarity measures. So here you can see z-scoring changes it, so it's mean 0, 1. So the little ones stay little, and the big ones, little ones get littler, and the big ones get bigger. So we're back to, here's the target. We're changing to a different target. Now we're on target 3, which I believe is a false negative. So this is actually belongs. It should look like the training samples. And so you can see how it is a dead ringer for the training samples. So we're moving the training samples around, the spatially close ones, and comparing them. And so we can just set them all up. And we also have a way, you can click a button and it all goes back to the original score plot as well. So here's the back side, because again, they're spheres, so we want to be able to move around the whole sphere and do them. So again, here's the z-scoring, and again, you can see that sometimes that helps, changes the glyph pattern a little, and it helps the human recognize the pattern better. So we have a couple different ways to change the glyphs around by our scaling. We also use probe samples, and that allows us also to change the glyphs. And the paper talks about our probe samples, but I'm not going to talk about it here. So I think he's deciding, we're going to finally decide that this is a true positive, not a false negative. So momentarily we'll open the hidden, it's now revealed. So when you touch it, you find out where it came from. You already have its z-score. You can see it's from the source, so it's clearly a true positive. So that's kind of how we did for this data set, the same table from the paper. We pick a couple, there's another split shown in the paper. We can't do all 50 splits. And you can see with our, like I said, we had different probes, and with the medium probe, we go straight up and down the board. All our false negatives and false positives become. As we say in the paper, our recommendation is you look at range scale, you look at z-scoring, the spikes, and across the different probes. So 4 probes, that gives you 8 views of the situation, and you just it's very you just click on the UI to change the view, and it helps decide what's going on. So you're looking for a consensus across all these views. So I always get asked this question, yeah, but what about the human biases? Because, like, as you've gathered, human is deciding what a sample is, whether it's in the class or out of the class. And so definitely there's biases, and we're all going to look at patterns different, but the obvious agreements are the true positives and true negatives, just like an autonomous algorithm would all agree on those pretty much. And those gray ones near the borderline, the thresholds that VR can come into play, and you can identify those based on if you can show your thresholds, know what your thresholds are in the VR. That's kind of tough for deep learning because the thresholds are set by optimizing the network, and then by the internal structure of the network, that's kind of like setting your thresholds. We didn't have to switch to UMAP, but there's other UMAP and other projection views you can also use. And I argue that computers are also just as much biased as humans are, because we all choose our algorithm. Do I want to use a tree structure for my classification? Do I want to use an artificial neural network? What do I want to use for it? And then there's the training of that to set your thresholds. And so these are sometimes set by the human, and therefore there are biases. So the structure, by choosing your algorithm, you're already incorporating human biases. That concludes our third application of virtual reality for one class classification, converting our false positives and negatives to true negatives and true positives.